So check this. We are given a question here. They say W is equal to X element of R such that X is greater than 0. And they say we must prove that the multiplication satisfies the engrams of scalar multiplication for a vector space. They only want us to check the scalar. Okay, let me check the whole question. They say the operation plus is defined on this, for this and this, and they say for all V element of W and a scalar element of R, prove that the multiplication satisfies the engrams of scalar multiplication for vector space. So now they want us to check scalar multiplication, right? So what you're going to do, guys, remember, first thing which you need to do to check is a closure under scalar multiplication. Don't do things you're not seeing here. First thing which you need to do, you need to pick some vector which is an element of W, right? You need to let V be an element of W. I'm picking a vector. After picking a vector, I must now equate W to this as it is. I must define it as it is. That's what they're going to check. I don't know if you guys, some of you haven't collected your quiz scripts, but if you collected, you might have seen what's happening there, right? So this will be equals to X element of R such that X is greater than 0. You letting V to be an element of W doesn't mean this is defined. You must define it. You must show us. You say, right? And we take a scalar to be an element of R such that when I take this scalar times V, I'm going to get, according to this, they say I'm getting V times that scale. And they say it's not V times the scalar. I'm going to get this. What is our V? Our V is X. So they're going to see if you use the X or not. So this will be X to the alpha. You see? And X is greater than 0. As long as X is greater than 0, this will always satisfy. This will always be greater than 0. Doesn't matter what this is. Right? If this, let's say X is 2, even if this is negative 1, this will always be 1 over 2, which is greater than 0. Even if this is 0, this will always be 1, which is great. We'll never get a negative number whenever we have this, or we'll never get a number which is 0 here. You say, right? So this will always satisfy. Or how do we check? It means that when we come here now, we must check if that condition satisfies. Check. We have this. We have this, which is an element of R. We know that this one will give us an R. But is this going to be greater than 0? You say, right? So that's what we must keep in mind. Is it going to be greater than 0? And we know that it's going to be greater than 0. So let me do this. So maybe let me re-explain it again, right? Maybe you can hear what I'm saying. First, you need to let some vector to be an element of W. Even they made things to be simple, they chose these two for us. After letting that vector to be an element of W, you must show that this is the case. You said you must equate that vector to that, to this. Whatever they'll be given you inside these curly brackets, you must equate it to that vector. And now you pick a scalar such that when you take that scalar times V, you are going to get scalar. What is our V? Our V is X. And this will be equal to X. According to that condition, it says X to the alpha. And you want to check if this will be greater than 0. Since we know that X is greater than 0, then also this will be greater than 0. You say, right? And indeed, such that this is true, such that X to the alpha is greater than 0. This will always be greater than 0. You say, right? This is true. Hence, if that is true, hence alpha V will be an element of W. You say, right? Now I've checked closure under scalar multiplication. Remember, after checking closure under scalar multiplication, what you need to check next, remember I said you need to check this condition where we have 1 times a vector, we must show if this is equals to 1. You see, right? You'll check what this, most of the times we call this monoid identity, but you'll check what they call it there. But this is SM10. So now when we come here to this one, we must let V be an element of W, such that we know that V will be equals to X, which is an element of R, such that X is greater than 0. And we pick now what we're 10, or let me not say we're not picking anything, we just need one vector for a monoid identity. We say then 1 times V will be equals to 1 times X. What is this? This is going to be X to the exponent 1, which we know that X is equals to V. You see, indeed we're getting a V here, so it shows that this one is satisfied. You see, right? So this monoid identity is satisfied. Then we check the other one. After this monoid identity, we can check this property, or if you don't know what the properties are named, you can say required to prove that. I'll start with this one. Remember, we have this property where we are adding vectors, but there's a scalar here. We add vectors u plus v. We are required to prove that this is equal to this. You see, right now? So first I need 2 vectors. I need to let v and u to be an element of W, such that I equate each to those values. This will be X element of R, such that X is greater than 0, and u will be equals to Y element of R, such that Y is greater than 0. And then actually, let me take a scalar. I didn't take a scale. I should take a scalar and let alpha be an element of R. Then we say then, if I take the left hand side, if I take alpha u plus v, I'm going to get alpha. Inside here I have our v, our u is equals to y, and our v is equals to x. Now let's check how did they say we are computing the ones of adding. They say when we're adding them, we must multiply. You see, right? When you're adding 2 things, you multiply. So the addition of these, according to that condition, this will be yx. And according to the condition of scalar multiplication, this will be yx to the exponent alpha. You see, right? And now we check the other side. We check the side where we're having alpha u plus alpha v, which this will be equals to. Let's check. This is alpha, this is y, alpha, this is x, and this will be, we can see which one to do first, right? Can I ask, should we do the scalar multiplication first or the vector addition first? Who can tell me which one should we do first? Scalar multiplication or vector addition first?
Vector.
Which one? Saying vector. Let's go and do vector. The vector one says that when I'm multiplying this, I'm going to have this, right? That's what the vector one is saying. And this will be y, and then I apply scalar, and this will be x, like that. You see, right? And now I can now factor out the scale. And we see that this side is equal to this side. Do you agree? And we see now that this implies that alpha u plus v is equal to alpha u plus alpha v. Now we check the fourth property. We're left with 2. These ones are similar. That's why I'm leaving them for the end term, right? We check the fourth property, which says that now I'm going to add the scalars times a vector, which I must show that this is equal to a scalar vector plus a scalar. Remember, a scalar should always be on the left hand side. So this is what I'm required to prove. I should have written here required to prove, right? Then now I must let one vector to be an element of W and to choose two scalars such that U is equal to U as Y, right? Y element of R such that Y is greater than 0. And I pick two scalars, alpha, beta, an element of R. And then, if I take the left hand side, this one, right? Which one do you think I'm gonna do first? Am I gonna apply the one of a vector or the scalars? Do we have any property where we're adding scalars here? Do we have anywhere on the definition where we're adding scalars?
No.
No. So it means that the scalars will keep them like that, and then we apply the vector, right? The scalar multiplication. So this will be like this. We won't add this two because there's no condition of adding scalars there. So we'll only do this. We'll say this is alpha plus beta. Do you agree?
Yes.
And we can try to drive this. If I drive this, this will be this plus. We keep, if the base are the same, we keep the base and add. No, not like this, man. Yeah, but it's like, let me do this before I come anywhere. It's supposed to be when they're multiplying. We keep the base, we apply the exponents properties. We keep the base and add the exponent. So this is the same thing as dropping that, right? Then from here, according to that one of vector addition, it says that when I'm adding two vectors, I can just multiply them. So this is the same. I can also separate them. I was skipping a step that time, so I wanted to show you according to that step. You say right. Remember that they say that if we're adding U plus V, we're going to get U times V. You see. So this is what happened. According to this will take us here. But according to this definition, since we are here, we can get here. That's why we are able to move from there to here. And this now we can drop with the scalar. We're taking it back. U plus this will be beta U. You say that right, ne? But what I'm doing here, it's not complete, because let me erase this and write it clearly now while I'm still explaining. What I was doing there is not complete. The reason being is because we are supposed to use, for our vector, we're supposed to substitute Y on U. You say right? Then this now will become Y to the alpha plus beta. If you feel like the rest will be difficult, take the other side. Take the other side. If you feel like changing that will be difficult, take the other side. Try to solve it. So when you come here, we're going to have alpha Y plus beta Y, right? And then from here, don't try to factor out anything. As long as there's no a property there of factoring out anything, don't try to factor out. Then from here, we can apply the vector addition. The vector addition says that when I'm adding two vectors, I'm going to multiply them. Then from here, I can now apply this on the exponent. I can apply the scalar multiplication. This is Y to the alpha, and this is Y to the beta. Then since that they're like this, we keep the base and add the exponents, alpha plus beta. We realize that the left hand side is equal to the right hand side. So I can say this implies that alpha plus beta U is equal to alpha U plus beta U. You say right. Now we prove the last one. The last one is simple, because remember with this one I was saying alpha plus beta. Here I'm just going to remove the plus, leave my beta there, which this will be equal to alpha beta U. The only difference now is that I'm going to interchange this. I'm going to take this, put it this side. This one comes first. You say right. This will be alpha beta U. Then I'll just erase this. That's according to the property. This one comes first. So I'm required to prove this. I need one vector. I'm going to let u to be an element of W such that u will be equals to y, which is an element of R, such that y is greater than 0. And I pick two scalars again. Let alpha, beta be an element of R. Then I take the left hand side. The left hand side is saying this alpha, beta, u, which this will be alpha, beta, y. Then when I apply inside here, this is going to be alpha, y to the beta. And this is going to be y, beta, alpha. You see, right? And then we get this. Now let's check the other side. According to that definition, this is according to that definition of scalar multiplication. When we check the other side, we have in alpha, beta times u. If we check this is just alpha, beta. We plug our y there. According to scalar multiplication, says that this will go to the exponent. This is y, alpha, beta. Even this one was supposed to be alpha, beta, which is the same thing. They can commute. You see, right? This shows that alpha, beta u is equal to alpha, beta u. Now, since these have been met, we have shown the question was prove the multiplication on, so it satisfies the enjoyment of scalar multiplication for a vector space. Then you can conclude that it does indeed satisfy the multiplication of that. Any question? Let me just stop this.